The topic of this video is polynomial multiplication. Specifically, we're going to be looking at multiplying polynomials using something called the area model, which you should be familiar with from Algebra 1. But we're going to go a little bit more in depth and kind of expand our scope a little bit for polynomial multiplication. So here are some examples. So we want to rewrite each of the following as a polynomial in standard form. And again, standard form meaning that our highest degree exponent will be first, all the way down to our constant term. What we have going on in problem number 1 is we've got x to the third minus 2x squared plus 6x minus 4 is being multiplied by the quantity 2x squared minus 5. To start with the area model, the first thing I want to do is I want to take my first polynomial here, which is x to the third minus 2x squared plus 6x minus 4, and just for convention's sake, I'm going to put that along the column. If I put it along the row, it wouldn't be wrong. It's whatever. We just see the first thing we see, we put it in the column. But if you switch them around, it really doesn't make a difference because we are performing multiplication. In the top row, I'm going to take my second polynomial, which is 2x squared minus 5. You may have noticed that in that particular polynomial, we don't have a linear term. What I'm going to do is put actually a placeholder in there, 2x squared, 0x, and minus 5. That's going to help me later when I actually need to do the multiplication and look to combine some like terms. So first thing I want to do then is try and figure out how are we actually going to do the multiplication. If I want to know what's in this box right here, I have to multiply the row and the column that meet. So I take x to the third times 2x squared, and that gives me 2x to the fifth. I can do the same thing for this box. Take negative 2x squared times 2x squared, that gives me negative 4x to the fourth. And I'll repeat that process for the entire column. So that's 12x to the third and negative 8x squared. So then I can take the next column and do the same thing. Here I'm going to distribute my 0x. So 0x times x to the third is 0. And I'm going to write it as x to the fourth, and you'll see why when we're looking at like terms later. 0x times negative 2x squared is 0x to the third, and then 0x squared and 0x. And finally, I take that negative 5 and distribute it through. Negative 5x to the third, 10x squared, negative 30x, and 20. And that completes the multiplication of the area model, but that's not my answer. My next step, once I've figured out what pieces go in the area model, is to actually make something out of it. And the way I'm going to do that is I'm actually going to put any like terms that I have together. So looking at my highest degree exponent, it looks like it's x to the fifth. So I don't see any other terms other than this first 2x to the fifth. So I know that's going to be part of my answer. I do notice that I have an x to the fourth next, and it's just strange that they kind of fit right there. I wonder if there's a pattern with that, which usually means there is. I'm going to then take this chunk, which is x to the thirds, and they also fall on a diagonal also. Interesting. And I can repeat that process using, will this one work? No, white is not a good highlighting color apparently. So try a different one. Let's just do blue here. And that's our x squared terms. I can finish this off using green for these guys here. And so the terms that are along the diagonal are my like terms. So my next step is to take those terms and actually put them together. So I start off with 2x to the fifth. That's my highest exponent. My next highest exponent is x to the fourth. Putting those two terms together, I get negative 4x to the fourth. Add my x to the thirds together, 12, 0, and negative 5 would give me 7x to the third. My x squared terms, I have a negative 8, a 0, and a 10. That would be 2x squared. And the x's together would give me negative 30x. And I have that term 20 at the very end. That's my final answer. I've put all my like terms together. Again, my like terms are on that diagonal. By putting that 0x in there, I maintain that diagonal of like terms. It made things a little bit easier. It's not necessary to put that 0x in there. It just helps keep everything in order. Let's look at another one where things might go a little bit different. We'll see. We're going to take number 5 here. We've got 3x plus 2 times the quantity 9x squared minus 6x plus 4. Just like I did before, I'm going to take that first expression, 3x plus 2, and put it along the column. Then I'm going to take my second polynomial and put it along the row. Now I need to fill out my area model, so I take 3x times 9x squared. That gives me 27x to the third. Completing that column, I've got 18x squared. I move on to my next column. 3x times negative 6x is negative 18x squared. Negative 6 times 2 is negative 12x. And finally, my last column, 3x times 4 is 12x, and 2 times 4 gives me 8. So, take my highlighter out again. Like terms along this diagonal, like terms along this diagonal. I'm looking to put those like terms together and get my final answer. So my first term is 27x to the third. My x squared terms actually cancel out. I've got a positive 18 and a negative 18. My x terms do the same. I've got a negative 12x and a positive 12x. And my last term is just plus 8. Strange. What happened was my quadratic term and my linear term were no more. What I was left with was my original cubic term and the term I had at the end, which is my constant term. But if you look more closely at each of the terms, 27x to the third, that number 27 is 3 cubed. The variable part x to the third is x taken to the third power. That is a perfect cube, as is 8. What we have is something called a sum of cubes. In other words, I take a perfect cube and I add it. What we're eventually going to do is take an expression like this and work backwards to that with the product of polynomials. And I'm going to demonstrate that in our next video, which is on division of polynomials. There are ways to factor it, but I think dividing polynomials makes things a little bit easier because it's not a little trick or anything we have to memorize. It's a process using division, which should be pretty straightforward. So again, multiplying with the area model, main idea is we've got to make sure that when we set these boxes up, that what we have here is correct. Once we've completed the area model, though, that's not our answer. It's the like terms along the diagonal added up. And that will give us a polynomial written out in standard form.